Okay, y'all. So last time we talked about matter and how we can classify matter into solids, liquids, or gases. Also, how we can classify matter based on pure substance or mixture. Now, today we're going to talk about changes that matter can undergo in the properties of matter. Changes in matter. Okay, so first we're going to talk about chemical changes. So a chemical change is a change that involves changing one or more substances into a new substance, and you cannot get the original substance back. So examples of this are burning something, rusting, cooking. So the key thing about a chemical change is a chemical reaction is required. So here's some common examples of some chemical changes. Once again, a chemical change requires a chemical reaction and things you cannot get back, right? So fireworks, it's like basically explosions. That's a chemical reaction. Frying an egg, you can't get back the original egg. That's a chemical reaction. The process of photosynthesis that you guys learned last year in biology. We got burning wood, combustion of propane, even digesting our food. I'm breaking down those food particles into something new by processes of chemical reactions. So here we are finally in chemistry saying chemical reaction. So a chemical reaction takes some sort or amount of reactants and turns it into some brand new things, products. So here's a classic chemical reaction. I have my reactants over here on the left-hand side, followed by an arrow showing the direction of the reaction, and then my products on the other side, the right side, okay? What happens in a chemical reaction is you notice that the hydrogen atoms and the oxygen atoms now come together and make a bond. Amazing. Okay, all chemical reactions, you've hopefully heard of this term before or this rule before. This is the law of conservation of mass, which just states that mass is neither created nor destroyed in a chemical reaction. That encompasses a lot of different information. One thing that law states then is that the total mass of my reactants has got to equal the total mass of my products. So back to my cute little formation of water equation that we saw in the previous slide here, where I have my hydrogen molecules and my oxygen molecules turn into two water molecules. One thing I'm looking here is I want the total mass to be the same on the reactant side and on the product side. So it looks like over here on the reactant side, I have 4 grams of hydrogen and 32 grams of oxygen. So that total, 4 plus 32, is hopefully 36, right? So that must mean that all of my products must mass 36 grams. That is what is stated in the law of conservation of mass. Another way to think about the law of conservation of mass is that the total number of atoms in your reactants has to equal the number of atoms in your product side. So looking at this on my reactant side, I can count the H's, 1, 2, 3, 4. I have 4 hydrogens. And then I also have 2 oxygens. That means no matter how all those atoms are rearranged and what bonds are broken and what bonds are formed, I better still have 4 hydrogens and 2 oxygens on the product side. That is me also still conserving mass. So here's a learning check on how good you are at the law of conservation of mass. So if reactant A and reactant B are combined to form product C, there are 3 grams of reactant A and 5 grams of reactant B. How many grams of product C are formed? I hope we can add 5 and 3 together, you guys. And I think that we just did a good job. So this is just the law of conservation of mass, right? Cool. All right. Now, if we're talking about chemical changes and chemical reactions, there are some things that we can actually visually see as a sign that a chemical change or a chemical reaction has occurred. The first one, if I see formation of light or fire, that is definitely a sign that a chemical reaction has occurred. If you'll remember my whoosh bottle on the first day of school, there was definitely some fire involved in there. That's absolutely a sign. Here is a piece of magnesium burning. We will see that tomorrow. That is a sign of chemical reaction. Another sign is a formation of an odor, right? If I randomly smell some weird odor out of nowhere, that means that something new was created, and that new thing may be a little bit stinky or have some sort of an odor. Then I also have an unexpected temperature change, meaning my reaction gets either really hot or really cold. Now, I do not mean mixing cold water and hot water together and being like, boom, temperature change, it is now lukewarm. No, I mean something unexpected, where you mix 2 room temperature type things and it just gets real cold or real hot. An unexpected color change. Once again, unexpected being the key word there. Do not mix something blue and yellow together and be like, whoa, color change, it turned green. No, I'm talking about something way, 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 way unexpected. This one, number 5, is a little bit wacky. You guys have probably not seen this term before, but it says formation of a precipitate. A precipitate is a specific thing when it comes to mixing two aqueous solutions together. I say aqueous because I'm country from Texas. You may hear people say aqueous. An aqueous solution is just any solution where you have a solute dissolved in water as the solvent. So if I mix two aqueous solutions together and I get something solid drop down to the bottom, that's called a precipitate. That's a sign that a chemical reaction has occurred. And we'll see a ton of those precipitation reactions this year in chemistry. And there's a whole lot to discover with that concept, which is very exciting and very cool. Okay, I'm moving on because I'm getting excited. Okay, the last sign of a chemical reaction, or last most common sign of a chemical reaction, is the formation of a gas. And I'm not talking about, I have boiled a pot of water and whoo, now there is water vapor. No, a gas that is not formed from evaporation or a basic phase change, okay? I'm talking about when I did my whoosh bottle, the first day of class, that whoosh sound that we heard was because I formed a gas, and a lot of it, that was trying to rapidly escape its container. All right. So that was chemical changes. So chemical changes need a chemical reaction to produce something new. Here we have a physical change. A physical change is something that does not change, or that changes that do not change the chemical composition of the substance. Okay? Examples of a simple physical change is a phase change. So here I have an ice cube. It is melting. I do not care if it is solid or liquid. This is still H2O. Ice is water in its solid form. Liquid water is still water, H2O, okay? Cutting something in half. Woo, I've just changed the shape of it. It is still paper if I've cut a piece of paper in half. Dissolving something in water. Do not be afraid that dissolving sounds like a super duper super sciencey word. I am just mixing something in water. If I were to evaporate the water, I would still have that same thing down at the bottom of my beaker. Mixing two substances together. We talked about mixtures the other day. We know that mixtures can be separated by physical means. Well, here we are. We're talking about physical changes, which just means I'm not causing anything chemically to happen with those two substances that I'm combining together. More examples of physical changes: melting, boiling, breaking a glass, it is still glass. Chopping wood, it is still wood. Folding paper, it is still paper. Breaking an egg, it is still an egg, even though it is in multiple parts. So as you can see in physical changes, I'm not changing what that substance is, okay? Now, it is time for us to talk about the phase changes between solid, liquid, and gases, okay? And the reason why we're talking about this here is because all of these words are physical changes, okay? Changing from one of my 3 different phases, I am not changing what the substance is. Let's use H2O as an example. I can have ice, H2O. It is still H2O. If I have liquid H2O, it is still H2O. If I have gas H2O, it is still H2O. The only difference is, if we'll go back to our last lesson, that it is changed in structure and in volume based on my solid, liquid, and gas properties, right? My water molecules, when they're in a gas, are just spread farther apart. So they're gases. And my water molecules as a solid, ice, are just closer together, okay? But they're still H2O. I have not broken apart the hydrogens and oxygens. Anyway, get it together, Sabaga. Let's talk about these terms. So hopefully going from a solid to a liquid, melting is not a new term for you. Hopefully going from a liquid back to a solid, freezing, is also a term that you are quite familiar with. Okay, going from a gas back down to a liquid is condensation, right? And going from a liquid to a gas, we could call that boiling, but the technical super sciencey chemistry term is vaporization or evaporation, right? The ones that we do not really talk about that much because they are not super common are the solid to gas and the gas to solid changes, okay? If I'm going from a solid to a gas, that's sublimation. If I'm going from a gas to a solid, that's called deposition. And the way that I remember these two terms, since they are not too frequently occurring, is that when I'm going from a solid to a gas, I'm going up to the sky. Work with me here. Like if I'm turning into a gas, I'm probably going up to the sky. So I think sublimation, which starts with an S, just like going up to the sky, which also starts with an S. Same thing, going from a gas to a solid, that's deposition. So gas to a solid is going down. Deposition, down. Sublimation, sky. Deposition, down. Y'all are like, whatever, Sabaka, but you're gonna remember it, so you're welcome. Okay, so the key thing about a physical change is it is usually reversible. The picture here is you bending a wire. I can bend that wire straight back to its original shape. I've not changed what that substance chemically is. Amazing. Learning check. Let's see how smart we are. You can pause the video right now and see if you can write these answers down. Amazing. We're going to go on. Let's see. Ice cream melting. I am zoning in on that phase change word. Melting. I don't care if it's ice cream. I don't care if it is a panda. I don't care if it is water. Pandas do not melt. Well, at high temperatures, pandas will melt. Anyway, I see melting. Phase change, that is simple physical change, right? Evaporating. Oh my gosh, another phase change word. Physical. Rusting. Rusting involves a chemical reaction. I have changed that metal into something new through the process of oxidation. That's a chemical change. Inflating a balloon. You've just made the balloon bigger. Physical change. Leaves changing color, going from green to the orange and the stuff. That's a chemical process going on inside of that leaf, right? Gasoline exploding. Wow, exploding sounds kind of chemically to me. Formation of pollutants. That process of pollution, creating pollutants in the air, is chemical changes. Dissolving salt in water. Once again, if you see dissolving anything, that is just mixing two things together. Amazing. So I think we're pretty good at that. All right. So we just talked about changes. Now we're going to talk about properties. So changes and properties actually kind of go hand in hand, and you'll see what I'm talking about here in a second. But just like with my changes where I had chemical and physical, with my properties, I also have chemical and physical. So let's start with chemical properties. Chemical properties are properties of a substance that can only be observed when it undergoes a chemical change. So in order to be observed as, it requires changing the composition of a substance. So examples of a chemical property of a substance would be how reactive it is, or reactivity, how flammable it is, or flammability, the heat of combustion, another way of saying the amount of energy required for it to react and combust with oxygen, the ability to oxidize, ability to decompose, basically just me picking up ways to describe a sample of a substance as it undergoes a chemical change. So all of these things are another examples of chemical properties, but in order for me to observe this from a substance, I have to observe it undergoing a chemical change or turning into something else. Okay, on the other hand, physical properties, they're just properties that can be observed or measured without changing what it is. Meaning I can look at it and I can measure it, and after I'm done observing that property, it is still the same thing. I have not chemically changed it into something else. So examples are like the length of something. If I measure a snake, first of all, I would not measure a snake because I would be scared of getting bitten by the snake. But if I were to measure a snake with a ruler, after I'm done measuring him, he would still be a snake, right? So things like length or mass or volume, or what color you are, or your density, or what temperature you happen to melt and boil at. And do not be freaked out by melting and boiling and think that that is a freaky thing. Y'all, those are terms to describe phase changes. We know in phase changes, you do not change what you are, right? So if I were to observe melting and boiling, that is just me not changing what the substance is, just watching it go through a phase change. What physical state it is, all of these things I can observe of a substance without turning it into something else. Here's some examples of physical properties. Nothing real weird, nothing real freaky. Okay, let's see how smart we are. You can pause the video now if you want a little bit extra practice. Okay, we're going on. Okay, let's see. Boiling point of water. Once again, boiling, phase change, physical. Okay, so me observing what temperature the water boils at is just me physically observing it undergo a phase change. Ice melting. Oh, melt. Another phase change word. You guys seeing a trend here? Phase changes are really important in this concept of this lesson that we're talking about today. Iron rusting. That is chemical. What color mercury happens to be? That's physical. I'm not going to change mercury based on observing its color. How stinky chlorine is. The odor of chlorine. That's physical. The mass of the earth. I can measure the mass of the earth without changing the earth. Physical. The ability of magnesium to burn. For me to check that out, I would have to watch magnesium burn, which would mean it would be undergoing a chemical reaction. And then finally, density of gold. That is physical. And we're going to talk about density a little bit more detail here at the end of the lesson. Okay, now I can further divide physical properties into two categories. I can divide them into either extensive or intensive. Extensive properties. An extensive property, once again, these are all physical, so I could say extensive physical properties are going to depend or change depending on the amount of matter that is present, okay? Like things like mass, length, volume, other kind of measured quantities that I can observe about something. So for example, the volume of water, that would be an extensive property. Volume's an extensive property. Let me give you an example. So if I have a teeny tiny glass of water versus a giant swimming pool of water, those volumes are going to be different. Water is still the same, right? But volume can change depending on how big of something I have or how small of something I have. Same thing with mass, right? If I have a ginormous block of iron versus an itty bitty teeny tiny small sliver of iron, that mass is going to be very different. It's still iron, right? So we would call mass an extensive property. Usually extensive properties are things that we can kind of measure and observe the differences based on size. Now, intensive properties are properties that do not depend on the amount of matter present in order to be observed. And as a result, they can be used to identify the composition of that substance. So, for example, going back to our water example where we had a cup of water and a swimming pool of water. The cup of water, smaller volume, swimming pool of water, larger volume. We know then by volume is going to be an extensive property because it depends on how big or small the sample is. But my cup of water, it's going to boil at 100 degrees Celsius. So is my swimming pool of water. I did not care how small my sample was or how big my sample was, but because they are both water, they're going to boil at the same temperature, okay? Same thing with like color. If I'm looking at the color of my glass of water and the color of my swimming pool, I'm like, okay, it's clear. I did not need a different size of the water for me to declare what the color of water is. So things, you guys, like density, we'll talk about density here in a second. I keep saying that. Y'all get excited. Like the temperature at which something melts or what boils. Heat capacity, meaning how much energy it takes for something to raise the temperature. How soluble something is in water. Basically, just things that just identify what a substance is independent of how big or small it is. And the way that I remember this, since intensive and extensive can be a little bit new for us and a little bit weird, is I say intensive properties are so intense that the amount of matter does not matter. And y'all are laughing, but guess what? Y'all are going to remember it, so you're welcome for that. So here's some example of intensive properties. They do not matter on the amount of matter that is present. So temperature at which something boils doesn't matter how big or small that sample is. The color of something doesn't matter how big or small. The temperature of something doesn't matter how big or small. If it is shiny, does not matter. If it is hard, does not matter if it is big or small. Versus these guys down here, my extensive properties, those things like volume and mass and size and weight and length, right? Stuff that I can usually measure, right, are going to change depending on the size of my sample of matter. But both of these categories, intensive and extensive, are just physical properties, things that I can observe without changing the substance through chemical means. Cool. Learning check. Are the following extensive or intensive? Let's see. All right. Melting point of water. Melting point of water. I don't care if you're a big sample of water or a small sample of water. You're going to melt at the same temperature. That is intensive. Length of a pencil. Big pencil, small pencil. That's going to be extensive. The mass of a block of wood. Big block of wood or small block of wood. That's going to change depending on the side. Extensive. The color of an apple. I don't care if it is a small apple or a large apple. That's going to be the same. And do not get all weird on me being like, well, what about the Granny Smith? No, we're just talking just normal, cute, like cartoon picture of an apple. The odor of sulfur, that's not going to change depending on the amount of sulfur present. And I have kids every year be like, well, it'll smell stinkier if it's a lot more of it. Yes, but what that specific odor is, like what scent your nose picks up, the degree or the intensity is not what I'm talking about there. It's just whatever the identity of that odor is. The density of gold is always going to be the same, no matter how big of a sample of gold you have or small. Volume is always extensive. Temperature is always intensive. Cool. Okay, here's a cute little flow chart. I thought this may be helpful for you guys if y'all wanted to look at this. Sounds good? Now let's talk about density. Density is not a new concept for you guys, but now we're going to talk about density in the terms of that physical intensive property that I've introduced here when I talked about intensive properties. So density by definition is a matter or a measure of how much mass is contained in a given volume. Now, a cool thing is that I can look at the three phases or three states of matter as a perfect representation of variation in density. So here with my little smiley face picture thing here, these guys are less dense than every other one of the things here, right? Because density is a measure of how much mass is contained in a given volume or how much stuff is in a certain amount of space. This guy right here, I don't have very many smiley faces in this same square block of space. But as I move this way, ooh, this one's got lots of smiley faces in the same square block of space. So this guy has more mass in the same amount of volume than this guy over here. If we were to look at these as the three phases of matter, this would be your gas, this would be your liquid, and that would be your solid. Okay, so this is when I'm going to switch to my document camera here, and we are going to go over the density lesson together. I know this is not the first time that you guys have calculated density. Y'all probably been doing this for forever, but we know in Miss Sabaka's chemistry class, we like to do things like show our work, and you better believe we're going to use the density equation to show our work here. Okay, density, D is equal to M over V. I think when y'all learn density, I think in Mrs. Martin's class, physicists tend to use the symbol rho for density, which looks like this little sideways P thingy, like a little lazy P. But chemists like to use the capital D version. So since we are chemists this year in my class, we're going to be using the capital D version. But once again, the equation actually kind of states what the definition of density is. It's how much mass you have in a certain amount of space or volume. So common units for mass are things like grams or milligrams, right? Sometimes we'll deal with pounds, but usually not, because we're scientists and we do not want to, use anything but the metric system. Volume are going to be things like liters, milliliters. You may see centimeters cubed. That 3 should be up here as a superscript. My bad, you guys. But the key thing here is centimeters cubed. 1 centimeters cubed is the exact same thing as 1 milliliter. So you can actually use those units interchangeably. You'll see that kind of frequently in some of our examples. So the units for density, because it is a mass value over a volume value, it's going to be mass per volume unit, okay? Now, it depends on what those units are going in, but the units coming out for density are going to be that ratio of those two things. Key thing here is that density is an intensive physical property. So when I say intensive, an intensive property is so intense the amount of matter does not matter. So if I tell you the density of water is 1 gram per milliliter, I do not care if you have a cup of water versus a swimming pool of water. The density of both of those things are going to be the same. Okay, and as a result, I can kind of identify a substance based on what its density is. I can go to a chart of all densities, and if I see the numerical values of densities of different substances, I can then identify what that is. And part of y'all's homework assignment on density will be dealing with that here in a little bit, which is super exciting. Okay, so it says, what is the density of an object that has a mass of 12.5 grams and a volume of 3.0 milliliters? Okay, I'm not an English teacher. I'm already like getting super overwhelmed. There's words here. And y'all are like, that's not a lot of words. I'm like, I'm old and tired. Too many words for me. I like my numbers here. So as a good chemistry student, I zone in all my numbers. I see a 12.5 and I see a 3. I always like to circle those numbers because those are my givens. Not only am I circling the number, I'm circling the unit behind it. So I've given you 12.5 grams and I've given you 3.0 milliliters, which is super exciting. Okay, and then I'm asking you to solve for the density. Now, this is our first like plug and chug equation that I've introduced to you guys here in chemistry. Now I'm going to show you the work that's required that I'm going to want to see for you showing appropriate work to get credit in my class for whenever I give you an equation to plug in and chug. I want to see you write down what equation are you going to use. Okay, so I need to see your equation. I cannot just see numbers on your page. I'm like, where do those numbers come from? Okay, so I'm seeing your equation. The next thing I need to see is the substitution into that equation, which means, okay, what mass value are you going to plug in? What volume value are you going to plug in? And guess what, you guys? Yes, they said mass of 12.5 grams and volume of 3.0 milliliters, but you cannot depend on those actual words of mass and volume leading into the number. What we are going to learn to depend on is the units here at the end. You see grams, you think mass immediately. I do not care what the words here look like. That is a mass value because it is grams. Same thing there. That is a volume value because I see milliliters. Okay? Now I can easily grab those two numbers and slam them in here. So my next thing I'm going to show you guys is me substituting the 12.5 on the top and then the volume on the bottom, right? But I do not just put 12.5. I must show the units in my substitution. And you guys are already rolling your eyes. You're like, you make me write so many things to like it. No, this is going to be useful. Just you wait. So 12.5 goes on the top. 3.0 milliliters goes on the bottom. So once again, I want to see what equation you're using. I want to see the substitution into the equation, okay? And then the last thing I want to see is your answer, obviously. But that answer needs to be rounded to the appropriate sig figs, and it needs to be in the appropriate units. So that part is nothing new. So then I grab my calculator. I was not prepared. Let me see if I have my calculator. I do have my calculator. Okay, here we go. Let's get her out. Let's see. There she is. So I'm ready to plug in these numbers. I have 12.5 divided by 3. My calculator gives me this, and you're like, cool, write down all those values. No, you must round your answer to sig figs, right? Well, this is a division thing, and we know when we multiply and divide, we round to the least amount of sig figs as the givens coming in. We have 2 of them to look at here. That one has 3 sig figs. 3 sig figs. This one has only 2 sig figs, right? So that means my answer has to be to the least number of sig figs. That means my answer has to be only 2 sig figs. So I want that 4. You can't even see. I want that 4. And I want that 1 behind it, but I got to round that 1 up because the 6 is telling me to. So I got 4.2. So my answer is 4.2. But I've not included the units. This is where showing your units in the substitution step is extremely useful, because it lets me know what my units are for density. We said up here that units are going to be some sort of mass over some sort of a volume unit. Well, here they are. We have grams per milliliters. So that is my answer. So with showing my work for density, this is what I'm going to want to look for. I want to see your equation. I want to see your substitution. And I want to see your answer. Okay? If you need to do other work around that, that is totally fine. But I need to see at least this. Okay? All right, so I'm going to bounce back to my PowerPoint slides now that we have learned about density. Oops, not like that. Let's see. Yeah. Okay, so we did this together. Amazing. The last thing I want to mention is I'm sure that you have done an experiment like this before, probably in IPC or physical science, where you've actually used water displacement to figure out what the volume of an object is of a weird shape. Like here's an example. I have a little screw. That's a very odd shape for me to, like with a ruler, estimate its length and height and width to calculate volume. So I can use volume displacement by actually dropping the screw in here and seeing how much that water has changed its height or that's volume to figure out what the overall volume of the object that I dropped in there. But the key thing with volume displacement is that to calculate that volume, I always take the final volume, where it's higher, minus the initial. Now, I think about it alphabetically. F for final comes before I in the alphabet. But then also, you guys, hopefully your final volume is a bigger number than your initial volume, to where you just subtract the ones from the other that does not give you a negative volume number. But the difference in volume for water displacement is always going to be your final minus your initial. So I think that's kind of it for pretty much all of Unit 2. I'm really excited, and I think it is just a fun little unit that we have gotten through together, and I cannot wait to see what is next.